on three dots, you will see.
Yeah, okay. Yeah, the recording has started.
Yeah, and after the class, you have to end the meeting and stop recording.
Yes.
Yeah, first stop recording, then end the meeting. Otherwise, the recording will go on.
Yes. Okay, so
I think you can start now.
today we'll be okay this. So today we'll be discussing the tutorial on eigenvalues and eigenvectors. The agenda will be the same. First, we'll be discussing the problems from that have been titled as tutorial problems. After each problem, I'll come back for doubts. So if you have any doubts in any of the problems that were discussed, please put them in the chat box and I'll uh, try to answer them after each question. So let's begin with question 1. Problem 1 was a good problem. What it says is that we have u, which is a unit vector in Rn, and they have defined a matrix H as I minus 2 times UU transpose. We need to find all the eigenvalues and eigenvectors of H, and also have to find the geometric interpretation of T of H, which is basically the linear transformation which is defined by H. So how do we go about it? The basic idea is that in order to find eigenvalues and eigenvectors, we need to have pairs of V, which is a vector in Rn, and lambda, which is a real number, such that H of V is equal to lambda times V. H is an n cross n matrix. V is a vector in Rn. R is lambda is a real number, and we need to have this. Then lambda will be the eigenvalue, and V will be a corresponding eigenvector. So how do we do this? We have this equation. H of V is equal to lambda times V. From the question, we bring in the definition of H. H was I minus 2 U transpose. U is a 2-dimensional matrix. So U is 2 cross 1 and U transpose is 1 cross 2. So U transpose will be a 2 cross 2 matrix. This I will be a 2 cross 2 identity matrix. So this is what has been defined as H, and we need to find V and lambda such that this equation holds true. So we just simplify this equation. We multiply V and get this equation. V minus 2 U transpose V is equal to lambda times V. And just rearranging so that we have this 1 minus lambda by 2 as a real number here, and this matrix U transpose here on the right hand side. So what does this say? That basically this is something, if you can imagine, this is something similar as finding the eigenvalues and eigenvectors of UU transpose. So if V is an eigenvector for UU transpose and lambda dash is the eigenvalue corresponding to this V for UU transpose, then based on the value of lambda dash, we can find lambda, that is lambda dash is equal to 1 minus lambda by 2. So this is what we will try to do. We will try to find V such that we get some sort of an eigenvalue eigenvector relationship. So one idea that comes to our mind is that U has been given as a unit vector. So what do we know? We know that U transpose U is 1. U transpose U is basically the dot product of U with itself. So basically it gives us the length of U, square of the length of U, which is again 1. So if we have multiply U transpose with U, this thing U transpose U will become 1. So what we do? We consider V as U. So right hand side was U transpose V. Put U as, put the value of U in V, and by association, like you associate it like this, U transpose is 1 because it was given that U was a unit vector. So U transpose V is equal to V because V is U. So this means that like for this we were trying to find lambda dash and V such that V is a eigenvector of U transpose and lambda dash was this. So lambda dash comes out to be 1 because we get U transpose times V is equal to V. So that, like, assume this is 1 here. So we have 1 minus lambda by 2 is equal to 1. So solving this, we get lambda equal to minus 1. So this gives us one pair that for lambda equal to minus 1, lambda is an eigenvalue of H and the corresponding eigenvector is U. Now an n cross n dimensional matrix will have n eigenvalues. Those eigenvalues, like among those n eigenvalues, they can be repeated. That is what the algebraic multiplicity gives us. But we'll have n eigenvalues, that's for sure. So how do we find what are the remaining eigenvectors and what are the remaining eigenvalues, and how many times does lambda equal to minus 1 occur as an eigenvalue for H? So how do we do that? What we do is we consider the n minus 1 dimensional subspace, call it W. This W is a subspace of Rn that contains all those vectors that are orthogonal to U. Now how do we get an intuitive idea about this? So we have U as a unit vector. So consider a basis of Rn. So we have n elements in that basis, and make that basis as an orthonormal basis. So U will be one element and all the other n minus 1 element in that basis will be unit vectors, and all of them will be orthogonal to each other. So that those n minus 1 vectors that we get apart from U in the basis of Rn, they'll form a subspace of Rn whose dimensions will be n minus 1, and any vector in that subspace will be orthogonal to U because any vector in that subspace could be written as a linear combination of those n minus 1 vectors, and all of those vectors are orthogonal to U because we had constructed an orthonormal basis. So that n minus 1 dimensional subspace that we get in such a way, we are calling it U. So what is the property of any element X that belongs to W? One is that it is orthogonal to U. That is, U transpose X is 0. This is by what I had said now. I'll just repeat it. So X belongs to that subspace. So X could be written as like a linear combination of those n minus 1 vectors. So say those vectors are v1, v2, v3 up to vn minus 1. So X will be some alpha 1 times v1 plus alpha 2 times v2 and so on till n minus 1. And with each of those, U transpose Vi will be 0. So U transpose X will be alpha 1 times U transpose V1 plus alpha 2 times U transpose V2 and so on. So we'll get this. So U transpose X equal to U, multiply both sides by U, pre-multiply both sides by U, and you get U transpose X equal to 0. And in that equation, equation number 4 here, for any X that belongs to W, we get U transpose is 0. So this one minus that lambda dash that we were talking about as an eigenvalue of U transpose, that becomes 0. So 1 minus lambda by 2 becomes 0, which means that lambda is 1. So now any element X in W follows this. So what does this mean? This means that all the element that W forms a basis. W is the eigenspace. Sorry, there's a mistake here. W is the basis, is not the basis. W is in itself the eigenspace corresponding to the eigenvalue 1, because every element in W follows this. Every element follows this. So what does this tell us? This tells us that W has n minus 1 dimensions. So the geometric multiplicity for lambda equal to 1 is n minus 1. And we also had the other value of lambda, that was minus 1. And minus 1 would have at least 1 as its geometric multiplicity, and sum of geometric multiplicities for lambda equal to 1 and lambda equal to -1, now we get as n, and it can't be more than n. So this means that the only eigenvalues of h are lambda is equal to 1, that comes n minus 1 times, and lambda equal to -1, that comes 1. So now the next part of the question was we needed to give an like idea about what the geometric interpretation of h is. So h is applied to v, that gives us v minus 2u transpose times v. So what is, let's understand what this u transpose v is. U transpose v can be written like this, u and u whole multiplied by u transpose v. Now u transpose v is the magnitude of the projection of u on u transpose. Why does this directly give us magnitude? It's because u is a unit vector, and that in direction, and this u gives it that direction. So u transpose v is basically the component of u which is in the direction of u. It's easy to visualize this considering 3 dimensions. Like in a 3-dimensional space, if you think about it, it becomes very easy to understand what is happening. So u transpose v is the component of v in the direction of u, and we are subtracting 2 times u transpose v from v. So what we are doing is we are reversing the direction of the component of v which is in the direction of u. So this is basically means that, consider we are in a 3-dimensional space and u is some unit vector in it. So if we reverse the direction of u, v, component of v that lies along u, we are basically taking the projection of v along the plane whose normal is u. Like in 3 dimension, it is very easy to visualize this. So in an n-dimensional space, a plane, like a 2-dimensional plane in a 3-dimensional, like if the total space is 3-dimensional, a plane is 2-dimensional. But if we have n dimensions, though it's not very easy to visualize, and the n-dimensional space that we get, which is orthogonal to u, is called an hyperplane. So just extrapolating what we have understood for 3 dimensions, what this equation v minus 2u transpose v is doing is basically it's reversing this direction of v along the plane. So we are taking the reflection of v in the plane which is defined by u. Defined by u means that u is orthogonal to that hyperplane. So this is basically the geometric interpretation of h. So this was question 1. This tutorial is not available on Bodhi. I think it is. It's tutorial 6, I believe, under eigenvalues and eigenvectors. Please have a look. Please check again. Next. So no one seems to be having any other doubts. So I'll move on to the next question. Problem 2 says that we have two matrices A and A dash which are n cross n dimensional, and this F could be either the space of real numbers or the space of complex numbers, and it says that A and A dash are similar. That is, there exists an invertible n cross n matrix P, again belonging to F n cross n, such that A dash is P inverse AP. We need to show two things. First thing is that A and A dash have same eigenvalues, and if V is an eigenvector of A, then P inverse V is an eigenvector of A dash. So we begin by solving the first problem. For any matrix M, let's just get an idea of how we'll go about proving A. For any matrix M, the eigenvalues are given by the roots of the characteristic polynomial. And what is the characteristic polynomial? It is basically the determinant of A minus lambda I, and we equate it to 0. So it's a function in lambda which will be n dimensional, because like we have lambda will get a power of n if we open the determinant of A minus lambda I. So if two matrices have the same characteristic polynomial, then their eigenvalues are same, because if they have same values, the roots of the same equations will be same, and we'll get the same values of the eigenvalues. So in order to prove that two matrices have the same eigenvalues, we just prove that their characteristic equation is same, and the characteristic equation is basically equating the characteristic polynomial to 0. So we, for A dash, we have determinant of P inverse AP minus lambda I, because A dash by definition is P inverse AP, because A and A dash are similar. So now we apply some rules or some properties of the determinant function. Determinant of P inverse AP minus lambda I. Now P inverse P is I. P is invertible and P inverse P is I by definition of inverse. So just like here I could be written as P inverse IP. Both these equations are same. And from this equation, it's just like A minus lambda I has been pre-multiplied by P inverse, and post-multiplied by P. Like on the left hand side, it's been multiplied by P inverse, and on the right hand side, it's been multiplied by P. So we get determinant of P inverse A multiplied by A minus lambda I times P equal to 0. Now using properties of determinant, the determinant of A, B is equal to determinant of A into determinant of B. We can separate this determinant into a product of three determinants. Determinant of P inverse into determinant of A minus lambda I into determinant of P. This is basically determinant of A minus lambda is basically the characteristic polynomial of A. So if we equate this equal to 0 and find its root, we'll get the eigenvalues for A. Now determinant of P and determinant of P inverse will be just like same, inverse of each other, and will cancel out each other. And obviously determinant of P is not equal to 0, so like we won't get 1 by 0 kind of division or anything, because P is invertible and is non-singular. So this reduces to determinant of A minus lambda I. So this is precisely, if we like equate this to 0, that continuation is here. So this is precisely the characteristic equation of A. So we have proved that the characteristic equation of A and A dash are same. So their eigenvalues will be same. Now the second part of the equation was V is an eigenvector of A. So what does this mean? V is an eigenvector of A, so it means that AV will be lambda V for some eigenvalue lambda. We needed to prove that P inverse is an eigenvalue of A dash, eigenvector of A dash. So let's just call P inverse V as U, just like to make the notation simpler. Now A dash times U is basically P inverse AP, which is A dash, times P inverse B, which is U. So now like just rearranging this, and by using properties of multiplication of matrices, we get P inverse A times P inverse B. Now this is equal to I, like P inverse P is equal to P inverse is equal to I, because that's the definition of an inverse. So, and in square matrices, this is how we, like this holds true. So this thing reduces to I, and we get P inverse A is as V, and again combine AV by using properties of the multiplication of matrices, we get P inverse AV. Now AV is equal to lambda V, because by definition V was an eigenvector of A and the corresponding eigenvalue was lambda. So we got P inverse lambda V, that is nothing else but equal to lambda U. So what have we proved? We have proved that A dash U is equal to lambda U, where U is P inverse V, and this is basically what the question asked us to prove, that P inverse V is indeed the eigenvector of A dash. Another thing that we have realized here is that if V has the eigenvector, V is an eigenvector of A and lambda is the corresponding eigenvalue, then for the same eigenvalue lambda, P inverse V will be the corresponding eigenvector for A dash. Now this lambda will indeed, like if A has an eigenvalue lambda, P inverse AP, that is A dash, will also have lambda as an eigenvalue as proved in part A. So that corresponding eigenvector will be P inverse V. So this is what the question asked us to prove. So are there any other?
Excuse me.
Yeah, who is speaking?
I'm Naman. This tutorial is not available on Bodhi Tree. Can you please check once again?
It's not, like the questions are different.
No, there is not an option of there is not any document named as tutorial 6 or something. There are only 3 lectures in eigenvalue and eigenvector.
Okay. So you're saying tutorial 6 has not been released? I don't know. I picked this up from Moodle itself.
But it is not visible to any of us.
Was it visible a few days ago? Because I picked it up this weekend and it was there. Okay, yeah, I can't see it on Bodhi Tree. Okay, so I'll make sure that it gets uploaded soon after this tutorial. But it will, okay, there has been some mistake, I believe, or because it was there this weekend. So okay, anyway, we'll just upload it soon after this. So I'll, like, you guys can continue, like, continue listening to the problems till then, because the concepts have been covered in class this past week. So this will give you an idea about, like, you can understand how these problems go about, and then you can try them yourself again. I have not covered the practice problems, and practice problems are quite similar to the tutorial problems, so you can try those yourselves, and if you have any doubts you can just message me on Teams, or yeah, message me on Teams regarding any doubts you have in the practice problems. So till then you can just ask me any questions that you have in the solutions that I give you, or any other doubts regarding to these problems. So I'll move to problem 3. Problem 3 has 3 parts. It says A is an n cross n matrix. We need to prove that 0 is an eigenvalue of A if and only if A is singular. So this is an if and only if statement. So we need to prove it in both directions. So how do we go about it? First we prove it in the forward direction. So 0 is an eigenvalue of A if and only if 0 is a root of the characteristic equation of A. So the characteristic equation of A is determinant of A minus lambda I equal to 0. So we put lambda equal to 0 because we want 0 to be an eigenvalue of A, and we get determinant of A equal to 0, that is A singular. Now for the reverse direction, if A is singular, we need to prove that 0 is an eigenvalue of A. So A is singular, that means determinant of A is 0. Like this can be just neatly written as A minus 0 times I equal to 0, which is same as the characteristic equation of A with lambda being put as 0. So what does this say? This simply means that if A is singular, then it has 0 as an eigenvalue. So we have proved it in both the directions. So we have proved the if and only if statement. The second part of the question was that if lambda is an eigenvalue of A, then it is also an eigenvalue of A transpose. So we need to prove that lambda is an eigenvalue of A and A transpose both if it is an eigenvalue of A. So by definition, the eigenvalues of A are the roots of the characteristic equation of A. So let's just call like this the characteristic equation function, which is subscripted by the matrix whose characteristic equation it is given. So for A, P of A is determinant of A minus xi, determinant of A minus xi. Now we are again using the properties of the determinant function. Determinant of A is equal to determinant of A transpose. So determinant of A minus xi is equal to determinant of A minus xi transpose. Take the take the transpose inside, like for A minus xi transpose is equal to A transpose minus xi transpose, and xi transpose is nothing else but xi. So we get determinant of A transpose minus xi, which is the characteristic equation of A transpose. So we have proved that P subscript A of x is same as P subscript A transpose of x. So both A and A transpose have the same characteristic equation and hence have the same eigenvalues. Now the third part of the question was to prove that if lambda is an eigenvalue of A and x is the corresponding eigenvector, then it is not necessary that x will be the eigenvector for A transpose corresponding to lambda. The eigenvalues of A and A transpose are same, but the corresponding eigenvectors need not always be same. So this is just like we'll prove this by giving a counter example. It's just a simple rule of mathematics that if you have to prove a statement, you need to generalize it and prove it for all the cases, like to the entire space to which that statement holds. And in order to disprove a statement, it's just enough to give one counter example where the statement does not hold. So we take a simple example of this matrix, this A skew symmetric matrix 0, 1, minus 1 and 0. So the characteristic equation, basically the determinant of A minus lambda, you'll get minus lambda and minus lambda here, take its determinant. So you get lambda square plus 1. Oh, there's a typo here, it should be 0. So the eigenvalues of A are the equations of lambda, roots of the equation lambda square plus 1 equal to 0, which gives us lambda is equal to plus minus 1. So let's find the eigenvector corresponding to plus minus iota. Sorry for that mistake. Plus minus to corresponding to iota, we get, say the eigenvector is x1, x2. So this means that A of x is equal to iota times x. So A minus iota x, A minus iota I x equal to 0. So what is A minus iota I? Iota 1, this is this matrix, multiply it by x and we find its solution. So its solutions, so it gives us two equations. You just solve this, like it's a very simple equation to solve. Multiply the first equation by iota and add them to get rid of x2, and we'll get the value of x1 as 1 and put it in either of the equations to get the value of x2 as iota. Now what were we supposed to prove? We were supposed to prove that A transpose x is not equal to iota times x. So what is A transpose x? A transpose is this. A was a skew symmetric matrix where we had minus 1 here. So you just multiply A transpose with x and we get minus iota and 1 as the elements of x. Now x is 1 and iota. This thing minus iota 1 is, you take out minus iota from it and you'll get 1 and iota, which is x. So we get A transpose x is equal to minus iota x and not iota x. So we have proved that x is not the eigenvector of A transpose corresponding to iota, but it is an eigenvector corresponding to minus iota. This is not a generalization, but it like if it's for A x corresponds to iota, then in A transpose X will correspond to minus iota. No, it's not like that, but we just needed to prove a counter. We just needed to prove that the statement was false. So we just proved it for one case, and in this case, as X comes out to be the eigenvector corresponding to minus iota, and that is enough in order to disprove the statement. Disproves the statement. This was problem 3. Anyone has any doubts? Okay, I don't see any doubts. So we'll move to next problem, problem 4. Problem 4 says we have a map, a linear transformation map from C superscript infinity 01 to C superscript infinity 01 given by T of f is basically the integration of f from 0 to x, and we have to prove that this map does not have any eigenvalue, while if instead of being an integration T was the differentiation operation, then every real number is an eigenvalue. So first, like this C infinity 01 is a symbol that has occurred before in tutorial number 4. So what it says, it is the set of all functions which are differentiable infinite times. Like you can have f dash x, f double dash x, f triple dash x, 4 times dash x. So you can just 4 derivative, 5 derivative, you can just keep on taking their derivative on 0 and 1. So this is basically the meaning of C C superscript infinity 0, 1. So in order to, we'll try to prove it by contradiction. So we'll have T of f as integration 0 to x ft dt. So let's assume that t has some eigenvalue which is called lambda. So what does it mean? T have an eigenvalue called lambda. So T of f will be equal to lambda f for at least one f. So f, obviously f should not be 0 because that will just be saying like 0 equal to 0, and we don't do that. So T of f x equal to lambda x. What was T of fx? T of fx was integration function by definition. So just put in there. Now just differentiate both sides. Now for differentiating both sides, what you will get? F of x into differentiation of x minus f of 0 into differentiation of 0, which is basically equal to f of x. And on the other side, we'll get differentiate this, lambda comes out of the differentiation as it's a constant, and we'll get f dash x. So if we just solve this differential equation, this is similar that you guys must have studied in school. So if lambda is an eigenvalue, this equation, if f follows this equation, it will be of the form f of x equal to f0 e raised to power x by lambda. Obviously lambda occurs in the denominator, so lambda cannot be equal to 0. So if lambda has an eigenvalue and f is a function that gives that eigenvalue lambda, f should be of the form this. Now this does not give us the answer right away. This does not mean that lambda is indeed an eigenvalue. Why? Because when we differentiated both sides, differentiation is basically we are like reducing the information content of the equation. So like for example, if we have say f of x is x plus 1 and g of x is x plus 2. So you need to find a solution of f of x equal to g of x. Of course, we know that x plus 1 and x plus 2 are two parallel lines and they won't have a solution. But if you differentiate them, you'll get 1 equal to 1. So you'll think that these two equations have infinite solutions. But that is not true, because by differentiation, you are reducing the information content. So it is a necessary condition, but it's not a sufficient condition. So if lambda is an eigenvalue, this is a necessary condition, but it's not a sufficient condition. So what do? We just put it in T of f. So we put this form of f, apply the transformation T to it. So we take that transformation was integration. So what do we get? We get this, you take out f from this integration of e raised to power x by lambda, you get e raised to power x by lambda minus 1, and this coefficient of x 1 by lambda, the inverse of which gets multiplied. So obviously this is not equal to lambda times f of x because of this minus 1 factor. So lambda is lambda for lambda not equal to 0. We don't have lambda as an eigenvalue of t. Now what about lambda equal to 0? So for lambda equal to 0, we would require integration of f of x as 0. If integration of f of x is 0, which that is only possible if if f is 0 on the entire domain. So this is again, like I said before, it's just like saying 0 equal to 0, and you do this like while defining eigenvalues and eigenvectors. This is not the correct way to do it. So we proved that lambda not equal to 0 is not an eigenvalue, and lambda equal to 0 is also not an eigenvalue. So no real number is an eigenvalue of this t. The next part was that if t was instead the differentiation function, that is t of f was d by dx of f, we need to prove that every real number is an eigenvalue. So what does it mean? Every real number is an eigenvalue, so it means that for any real number lambda, there will be at least one f such that t of f equal to lambda times f. So t of f equal to lambda times f. T of f is f dash x. So f dash x is equal to lambda times f. So we just solve this differential equation as we had done before, and this time we get f of x is f of 0 into e power lambda x. F of 0 is just like comes because of those limits, like you integrated from 0 to x or something like that. So you'll get a, like I put the limits from 0 to x, so you got f of 0. You could do something other than that, and then you could have this, like you'll have, if you put in x limits from x, say y to x, so you'll have in the exponential part, you'll also have a minus y factor and so on. So just 0 is just a neat limit to put. So for such a function f, we again, as we had done before, we put it in the equation. So for t of f this time, we get t of f indeed as lambda times f of x, because f0 differentiation of f0 e power lambda x is nothing. This lambda just comes out, lambda times f0 e power lambda x, because d by dx of e power x equal to e power x. So we have proved that for every lambda, there will be any real number lambda, there will be at least one function that satisfies this t of f is equal to lambda times f. So all real numbers are an eigenvalue for t. So since t holds for all real values, every real number is an eigenvalue of t. So this was problem number 4. Okay, so are there any doubts? Okay, so I don't see any doubts, so I'll move on to problem number 5. Problem number 5 was a good problem. It says that A belongs to C n cross n. A is an n cross n matrix, and f of x is a complex polynomial, which is this is the polynomial, and we need to prove that if lambda is an eigenvalue of A, f of lambda is an eigenvalue of f of A, and we also need to find all the eigenvalues of f of A. So f of, just writing it out again, f of A is a raised to power n plus some complex numbers a n minus 1, a raised to power n minus 1, and so on. And similarly, f of lambda is this. So note, f of A belongs to C n cross n, and f of lambda belongs to C. So suppose V be the eigenvector of A corresponding to the eigenvalue lambda. So we have A of V equal to lambda of V. So in order to prove this question, what the question asks us, we'll prove 3 things. The first thing is, you just observe that if we have AV equal to lambda V, you pre-multiply both sides by A. So you'll get A square V is equal to you'll get a square v as a of a into v, and a into v is lambda v. So you bring out lambda and you rearrange this to get lambda times a of v. A of v is again equal to lambda v, so you get lambda square v. So a square v is equal to lambda square v. You just keep on doing this for any value of, like you just pre-multiply this by a any number of times, and you will get a of a raised to power iv is equal to lambda raised to power iv. So what does this mean? A raised to a, this thing we have shown that a square has an eigenvalue lambda square. So you just keep on doing this and like just prove it by induction or just observe it. You will get that lambda raised to power I is an eigenvalue of a raised to power I, and the corresponding eigenvector v remains the same. The second thing that we prove is that if we have two matrices A1 and A2 which have a same eigenvector V, though the corresponding eigenvalues lambda 1 and lambda 2 could be different, and we define another matrix Q which is A1 plus A2. Now Q will have for the eigenvector V for A1 and A2, V will also be an eigenvector of Q, and the corresponding eigenvalues will be lambda 1 plus lambda 2. So it's just simple math. Q of V is A1 plus A2 times V, which is equal to lambda 1 plus lambda 2 times V. Now the third thing that we prove is that if you multiply A by scalar, so B is equal to AV, and V is an eigenvector of A and the corresponding eigenvalue is lambda. So B of V will be A times capital A, like this scalar multiplied by this matrix into V, which is nothing but A lambda V. So for B, A times lambda is the eigenvalue and the corresponding eigenvector remains the same. So in all these three things, we have proved that the eigenvector remains the same. So combine all those three things. So fa of v is, you just like bring in v, like this thing would be whole multiplied by v, and you can just separate it out based on properties of multiplication of matrix. So what do we know that a v is equal to lambda v. So v is an eigenvalue of a corresponding eigenvector of a corresponding to lambda. So by the first thing that we have proved, this a of n v turns out to be lambda n v. Now for a n minus 1, a n minus capital A n minus 1 times v. So for a n minus 1 matrix, lambda n minus 1 would be the eigenvalue corresponding to v by property 1 that we have proved, and this is using this scalar multiplication, the property 3 that we have proved, we get this. Similarly for n minus 2, n minus 3 up to n minus 1 up to 1, and for a0 it just remains the same because there is no a attached here. So this is nothing but f of lambda times v. You just take v out common, and what you will find is that lambda v, f of lambda remains. So what we have proved, f of a times v is equal to f of lambda times v. So f of lambda is the eigenvalue for f of a corresponding to v. So from this we can clearly see that if lambda 1, lambda 2 up to lambda n are the eigenvalues of a, so then the eigenvalues of f of a, so this set f of lambda 1, f of lambda 2 up to f of lambda n, all of them will be eigenvalues of a. And since the dimensions of a and f of a are same, both are n cross n matrices, they should have the same number of eigenvalues. So we'll have n eigenvalues. They could be repeated, but in total they'd be n eigenvalues. So this means that all the eigenvalues of f of a are of the form of f of lambda, because this set contains n elements. Like those elements could be repeated, but there would be a total of n elements, and each of them is an eigenvalue of f of a, and there are n such elements. So every eigenvalue will be of the form of f of lambda. So this was problem 5. Are there any doubts? Okay, no, there aren't any doubts. I'll move on to the next question. Problem 6 is similar to part of the problem number 3 or something we have proved earlier. So I'll just quickly go over it again. In order, we have to prove that A and A transpose have the same characteristic polynomial and hence they have the same equation. The eigenvalues of A are the roots of the characteristic equation of A. So the characteristic polynomial of A is determinant of A minus xi, if we choose to call that variable for that equation as x, polynomial as x. So just using the property that determinant of A is equal to determinant of A transpose and taking this transpose inside, we get determinant of A transpose minus xa is equal to determinant of A minus xa, which is this determinant of A transpose minus xa. It's nothing else but the characteristic polynomial of A transpose. So both of them have the same characteristic polynomial. Equate the characteristic polynomial to 0 to get the characteristic equation. So characteristic equation of A and characteristic equation of A transpose are same, and so because those equations are same, their roots would be same. The solutions of those equations would be same, and hence those solutions, which are nothing else but the eigenvalues of A and A transpose, they would be same. So this was problem 6. I hope no one has a doubt in it. Okay. So next is problem number 7. Problem number 7 says that find the characteristic polynomial, eigenspaces and dimensions of a matrix Jn. Jn has been, J subscript n has been described as an n cross n matrix in which every entry is 1. So n cross n matrix consisting of all n, all ones. So we need to find the characteristic polynomial, eigenspaces and their dimension and the dimensions. So the second part of the question is if we need to find if J is diagonalizable or not. So let's just understand what J is doing. So we have any eigenvalue and any vector V in Rn. So it will be V1, V2 up to Vn. Apply J to V. So this is a vector matrix of all 1 and we multiply it by V1, V2, Vn. So what is happening in the first element, the first n, like Jn is n cross n, apply it to n cross 1. So we get an n cross 1. So Jn would be indeed an n cross 1 vector. And you find that each element is summation of all the elements of V. So V1 plus V2 plus Vn. So all the elements of the result of Jn will be this. So just pull out that scalar and we get a vector of all ones multiplied by this scalar. So in order to have J of n V is equal to lambda V, V should be of the form of A times 1. This bold 1 is a vector of all ones, n-dimensional vector of all ones. Why is this so? Because for any V, Jn of V will be equal to some scalar times 1. So in order to have the same V on both right hand side and left hand side, on right hand side we also need to provide some A times 1. A times vector of all ones. So we prove we put in A times vector of all ones, and this summation of Vi would then become n times A. So this A of 1 will be remain the eigenvector and that n will become the eigenvalue. So that n is the eigenvalue and the corresponding one of the corresponding eigenvectors is this vector of all ones, and any other scalar multiple of that eigenvector obviously would also be an eigenvector for n eigenvalue. So what are the remaining eigenvalues? So determinant of Jn is 0. Why? Because all the rows are same and we know that exchanging two rows should flip the sign of the determinant, and it does not do so in such a case, in this case, because all the rows are same. So Jn is a singular matrix. So it has 0 as an eigenvalue because Jn is singular. This was part 1 of a 3-part problem that we have proved earlier. So Jn is singular and hence has 0 as an eigenvalue. Now let's try to find the row echelon form of J. So what do we need to do? We need to have one pivot column, and what we'll get, we perform these equations. Subtract row 1 from all the remaining n minus 1 rows. So row 2 minus row 1, row 3 minus row 1, do all these equations. Now, since all the rows are same, all the other rows on which we had applied this operation, that is R2, R3 up to Rn, they'll become 0, and only R1 will remain as a row of all ones. So this gives us a matrix whose first row is all ones and all other elements are 0. So this means that rank of Jn is 1 because only we'll have one pivot column, and the nullity is n minus 1, invoking the rank nullity theorem, and J, because we know Jn is an n cross n matrix. So the dimension of null space of n is n minus 1 by definition of nullity. The dimension of n null space of Jn is n minus 1. Now the eigenspace corresponding to the eigenvalue 0. We have proved earlier that 0 is an eigenvalue of Jn. So we need to, what is the eigenspace corresponding to eigenvalue 0? It is basically the set of all vectors such that Jn of v equal to 0, which is nothing else but the null space of Jn. So the dimension of the null space of Jn is same as the dimension of the eigenspace corresponding to eigenvalue 0, which is n minus 1. So now we'll use some interesting results. We know that the sum of algebraic multiplicities of Jn is n. What is algebraic multiplicity? It basically means how many times algebraic multiplicity of an eigenvalue is basically the number of times that eigenvalue comes in the character, is repeated in lambda is repeated in the characteristic polynomial. So if it's a doubly repeated root, then for example, if the characteristic polynomial is x minus 1 whole square, so then 1 will be an eigenvalue and its algebraic multiplicity will be 2. So we know that's because a characteristic polynomial is a polynomial of power n, so we'll have n roots. So the sum of algebraic multiplicities will be n. And in class, it has also been proved that the sum of geometric, we know that geometric multiplicity of an eigenvalue is less than the algebraic multiplicity of that eigenvalue. So sum over all the eigenvalues to get that sum of geometric multiplicities of all eigenvalues of Jn will be less than equal to sum of algebraic multiplicities of all eigenvalues of Jn. Now algebraic multiplicities ka sum is n. So we get geometric multiplicity, sum of geometric multiplicities is less than equal to n. So in the last slide, we have proved that geometric multiplicity of 0 was n minus 1. What was geometric multiplicity? Geometric multiplicity is the dimension of the eigenspace corresponding to that eigenvalue. So for eigenvalue 0, we had proved that the eigenspace will be n minus 1 dimensional. So using the above inequality, that geometric multiplicity should be less than equal to 1. So geometric multiplicity for the other eigenvalue n that we have proved in the first slide of this problem should be less than equal to 1. But it is an eigenvalue, and one of the dimensions that belongs to its eigenspace is the vector corresponding to all ones. Like it has at least one eigenvector. So it means that this eigenspace for the eigenvalue n would have at least one dimensional basis. So we get this result that geometric multiplicity of n is greater than equal to 1 just by its existence, and it should be less than equal to 1 by this equation. So what do we get? Both these inequalities give us that the geometric multiplicity of n should be 1. So from the above discussion, we get that the algebraic multiplicity of 0 is n minus 1, and that of n minus 1 is, and that of n is 1. One part of the question also asked us to find the characteristic polynomial of n. Characteristic polynomial can now simply be found as lambda minus n into lambda raised to power n minus 1, because n eigenvalue has an algebraic multiplicity of 1 and 0 has an algebraic multiplicity of n minus 1. How are we making these assumptions, these statements about algebraic multiplicity when we had proved them about geometric multiplicity? That is because geometric multiplicity is less than equal to algebraic multiplicity, but these equalities hold. This sum of geometric multiplicities is equal to n holds only when each of the corresponding geometric multiplicity would be equal to algebraic multiplicity. So this would give us that the characteristic polynomial of Jn as this expression which is written here. Now we also had to find the eigenspaces correspondingly. So the eigenspace corresponding to the eigenvalue n is the vector of all ones, like one of the eigenvectors. So one vector, and it is a one-dimensional space as proved earlier. So we can just give one as an eigenbasis, like one as a basis of that eigenspace. For the n minus one dimensional space, null space. So we find this n minus one dimensional basis for the eigenspace corresponding to the eigenvalue 0. So how do we do that? You do that by finding the equation, by finding the roots, by finding the basis for ax equal to 0. So how do we do? You just put x1 equal to 1. Like if x is x1, x2, xn, you put x1 equal to 1. And for the first special value, you put x2 as minus 1 and all other elements, all other n minus 2 elements as 0. For the second element in that basis, you put x2 as minus 1 and all the other elements are 0. Because ax equal to 0, what does it say? It just says that summation xi equal to 0, because all the elements of Jn is equal to 0 now. So you just put in these special values and you'll get one, like one of the bases. Obviously this basis is not unique. You can just put in different special values and get different bases, and there'll be n minus 1 elements in this basis. So this is a basis of this eigenspace, and any element that belongs to this eigenspace can be written as a linear combination of these elements, and every linear combination of these elements will belong to that eigenspace. Now another result, important result that has been proved in class is that for every eigenspace, if we take their dimensions and sum them, we should get n if and only if J is diagonalizable. So this has been proved in class, and for our matrix Jn, we have proved that the sum of the dimensions of the eigenspaces is indeed 1 plus n minus 1, which is n. So Jn is diagonalizable. That was question number 7. Okay, I don't see any doubts, so I'll move on to the next question. This is the last question of this tutorial. This is a relatively simpler problem. So we say that U and V is an orthonormal basis of R2, and and we define a matrix 2 cross 2 matrix A as UV transpose. Now we need to find all the eigenvalues of A. So since U and V belong to R2, we can just write U as some AB, like where A and B are real numbers. So U and V are an orthonormal basis. So both of these U and V are unit vectors. So we get A square plus B square equal to 1. So if we have this, we also need to assume V. So assume V is xy. So we have two conditions now. V is a unit vector, so x square plus y square would be 1, and U and V are orthogonal to each other. So V transpose U should be equal to 0. So you'll get xa plus yb equal to 0 and x square plus y square equal to 1. So you just like have a look at these equations and you'll realize that x and y should be of this form: cb and minus ca, where c is either plus 1 or minus 1. So the two equations we had was ax plus by equal to 0. So this will give us x by y is equal to minus b by a, and x squared plus y square equal to 1 is the other equation that we get by virtue of v being a unit vector. So you just put that x by y in this x squared plus y square equal to 1 to get this kind of result. So if v is of the form cb and minus ca, what will A be? A is UV transpose, and if you just multiply out these 4 elements, you'll get this 2 cross 2 matrix. So in order to find the eigenvalues of A, we need to find the roots of the characteristic polynomial. So characteristic polynomial is determinant of A minus lambda I, which is this equation, and it's a 2 cross 2 matrix, so you just simply open it out. This just means this gives us this equation, CAB minus lambda into negative of CAB plus lambda plus C square A square B square, and you just simplify it, use the property A minus B plus B equal to A square minus B square, cancel these out to get lambda square. So equating the characteristic polynomial to 0, lambda square equal to 0, this gives us the eigenvalues as 0, and the algebraic multiplicity is 2 because it is being repeated twice, and a 2 cross 2 dimensional matrix will have only 2 eigenvalues and both of them are 0, so 0 is the only eigenvalue. So this was problem number 8. Are there any doubts? Okay, I don't see any doubts, and we are also almost out of time, so I'll end this tutorial here. And since most of you haven't been able to practice these problems, I'll leave all the practice problems for your own self, so you can try those out, and if you have any doubts you can just message me. So I'll stop the recording and we can end this meeting.